Well, can you provide that link on to the pulsars at this point?
Yes.
Is that the next story?
That's the next story. Well, I developed the interplanetary scintillation technology. I use that as a tool to measure angular sizes of radio galaxies. I can't go into the details, but essentially the scintillation varies strongly as you look at a particular source. When it's close to the sun or whether it's far from the sun, you get much more scintillation when it's near the sun than when it's far away. And if you apply diffraction theory to that, you can see that this is a method for actually measure angular sizes with an angular resolving power, which is much, much higher than you can get with any sensible radio telescope. But the wavelength I was observing the scintillation on, I could get in principle, an angular resolving power, which would otherwise require a radio telescope bigger than the diameter of the Earth. With interferometers, you can get very high angular resolving power, but with scintillation, you can do very much better. And I thought, well, we were then beginning to understand more about quasars, and in Martin Rao's surveys of the sky, 1,000 or so radio galaxies were then known, the positions of them, but it wasn't known really what the radio galaxies were. But quasars had been discovered, one or two quasars, which have the property that they have a very bright nucleus and they send jets in different directions, and they do have they have components which are a very tiny angular size, and it is those components that twinkle. And I thought, well, let us carry out a sky survey to see which of the 1,000 radio galaxies are the most interesting ones astrophysically, which are the quasars of this 1,000. Now, I could do that by seeing which ones scintillated most strongly, and I could actually measure angular sizes. I developed the technology then, the theory of the scintillation, to use this twinkling in the solar wind to measure angular size quantitatively. And I set up a survey to do this for about 1,000 radio galaxies. But it required a very unusual instrument. It had to be sensitive to see enough radio galaxies. It had to be working on a longish wavelength, which is where the twinkling shows up best. And it wasn't like any existing radio telescope. So essentially I had to build my own telescope, which consisted ultimately of 2,000 dipoles spread over a 4-acre field. And it observed the radio sources as they crossed the meridian. And according to how much or how little they scintillated, I could measure the angular sizes and sort out fairly quickly which ones were quasars and therefore deserving of further studies, and which ones were just sort of standard radio galaxies, you might say. And so I set up, I planned a survey which was operating actually in 1967. I planned it in 1964-65 as an extension of the work I've been doing, just to make a complete sky survey of scintillating sources, and to sort out the quasars from the non-quasars. And it was during that survey that the pulsars turned up. But this was a telescope that we could build with our own effort, not too expensively, on the site itself. I mean, in present day funding, it would have cost about £1 million, I suppose, or something like that. In those days, it cost about £20,000. £500,000 would have been more like it. But this was something we could get on with our own effort. Once again, you could persuade the committee quite quickly that this was worthwhile doing, and I got the funding within 6 months, and was planning the telescope in 65, and it was completed in 67, and that's when the Sky Survey began. And with that technology, with that instrument, it was impossible really to avoid detecting pulsars. They were just tailor-made I mean, the instrument was tailor-made to discover pulsars because the fluctuations of pulsars are in just the same time scale as the scintillations I was looking at, so you had to see them. And that's what happened.
I always tell people that the message came along a wire which came in through the window of the aforesaid room in Lloyd Science. Did it come along a wire from the computer into the room?
We weren't using computers at all, as a matter of fact. It came along coaxial cables.
Oh, cables, yes.
And it went onto pen recorders for reasons of economy and also speed. Digital recording of the quantity of data that I was handling then, I was handling a large quantity of data, wasn't really a very practical solution.
So it
was quicker
pen.
and cheaper to have pen recordings, and so we had initially 3, later 4 paper charts, just like electrocardiograms, and it was my industrious student Jocelyn who had the task of analysing all these paper charts, and she, as I'm sure you know, was the first to actually see something strange going on these paper charts.
Can you remember what she said? She said, "I see something strange, Antony," or what did?
Well, it's actually it's a slightly longer story than that. Popular science says she suddenly saw pulses, which isn't true. What we saw was a source which was showing. Initially, she pointed out to me a record. She says, here's a source that looks a bit funny because it's showing too much scintillation in the middle of the night. Now, in the middle of the night, you're not looking through a dense part of the solar wind. You're looking in the anti-solar direction. And the solar wind, of course, its density varies inversely as the square of the distance from the sun. So when you're looking backwards, as it were, from the Earth, you look through a much less dense region of the solar wind. And normally, our radio galaxies, whatever they were, only scintillated at about the 10% level. And what she noticed was that there was a rather faint source scintillating at the 100% level. This was evident from the sort of recordings we took. I mean, you only needed to glance at it to see that here was something a bit unusual. What is it scintillating 100% in the anti-solar direction? And we didn't know what it was. We didn't know whether, first of all, it was even a genuine signal. But after it had reappeared, we surveyed the whole sky roughly once a week, and it had appeared 2 or 3 times. Sometimes it wasn't there at all, which was another mystery, and neither of us fully believed it, that it was a genuine source. But I said, well, let's have a closer look. It could be something like the initial radiation from the sun, which was discovered by Hay, as we've mentioned earlier. Perhaps there are radio galaxies, perhaps, I don't mean radio galaxies, perhaps there are stars in our own galaxy, which are a bit like the sun, but a bit further off, which occasionally show fluctuating signals, radiate sort of intense noise when there are sunspots on them. I mean, the sun isn't a particularly unique object. There are lots of stars like the sun, so you'd expect to see more like that. And but I realised that the radiation that we would get from such a source wouldn't look like the normal interplanetary scintillation. So I said, we've got to get a closer look at this and run a fast record and see, in fact, have a close look at those scintillations to see just what is the time structure of them. And so that's what we did. And that's how the pulses turned up. It took a little while. It took 2 or 3 months to get some good recordings. But when we looked at the fluctuations more closely on this peculiar source that Jocelyn pointed out to me, then it was clear that they were pulsing, and that was a shattering blow, really. What on earth could be doing that? It was clearly well, we discovered pretty soon it had to be beyond the nearby stars, but not too far. It was way out in our own galaxy, but it was a stellar source, and all kinds of thoughts went through our minds.
Yes.
I mean, it was such an artificial signal that I had to seriously consider, is somebody actually sending a signal to us? It didn't seem to be coded in any way, but it wasn't impossible by any means. And we could measure the size of the object launching the signal. It couldn't have been larger than a planet. So we had the problem, regular flashing signals from an object which is of planetary size or less. And what on earth can it be? And
how close were you to breaking this news to the ever hopeful press that you had discovered little green men?
Very wary not to do that.
Yes.
We kept our mouths tightly shut because we'd already had our fingers burnt this way. Way back in 1957, we were the first group of radio astronomers to locate the Russian Sputnik. Everybody knew it was up there because you could hear it bleeping, but nobody quite knew where it was. And we set up a simple interferometer. I wasn't involved with this particular work, but we set up a simple interferometer here just at the old rifle range, just a few miles away from where we're sitting, and got the rough orbit of the first Russian Sputnik. And the press descended in hordes on the old Cavendish, on the rifle range there, and filled the lab, asking stupid questions and tripping over cables, and normal work was quite impossible. And that was just confirming that the Russians had actually sent up a satellite, and where it was, an Earth orbiting satellite. And that attracted hordes and hordes of the press. They couldn't detect it at Jodrell Bank because they didn't know where it was, you see, and it crosses the sky in about 90 minutes. And if you've got a 250-foot dish, you know, to hunt around, you just can't catch it. And but when we sent the position to Jodrell Bank, they picked it up immediately. And then the press, of course, all got in their cars and went off to Jodrell Bank. But the point was, here we had a real mystery at Lord's Bridge. And the moment anything leaked out that we were picking up something strange, possibly even intelligence, what would have happened? The place would have filled instantly with the press. I mean, you couldn't have avoided it. And I was dead keen myself that we should get on with the science quietly and deliberately, without being bothered by people asking stupid questions and getting it all wrong and blazing publicity all over the world. I had a test for checking the little green men idea. I had to pinch myself actually to really take this seriously, I admit. But I was made to think seriously about this by, I don't know if the name Teddy Bullard means anything to do, the late Sir Edward Bullard, a famous geophysicist. It was a bit frustrating for me in these exciting days because I had to spend a week closeted in my room in Churchill College marking the scholarship exam. we had an open scholarship exam in those days, I'm sure you'll remember, and these had to be marked quickly and immediately, and that meant the full-time work for about a week marking scholarship papers, and that was almost directly after the first pulse had actually appeared on the records. The first pulse appeared on November the 28th, and the scholarship exam was about the 1st of December, so I was very busy, tied up in Churchill College, and I was having lunch there one day, and sitting next to Teddy Bullard, and I quietly mentioned to him the fact that we were picking up these unusual pulses, and what did he think about it? And he said, well, if they're narrowband, they're probably intelligence. Very wise remark. And so he took it seriously, and I had to take it seriously. And we were, in fact, already measuring the bandwidth, and they were indeed narrowband signals instantaneously. But my argument was that if you have intelligent signals, they're likely to be coming from a planet, and a planet has to be in orbit about a star. So by then, working in my room in the old Cavendish and doing careful timing of these pulses, I'd already discovered that they were keeping time to better than a millionth of a second per day, and I realized that I could detect planetary orbital motion very quickly if they were coming from a planet in orbit about some distant sun. And so I set up measurements to do that. I timed the pulses accurately for, well, I did it in the end for just about a month. But I decided that if I could detect this planetary orbital motion using what we call the Doppler shift, as the planet accelerates towards and away from the Earth, you can detect that by what we call the Doppler shift by careful timing measurements. And I set up timing measurements and carried these out myself for several weeks, and ultimately discovered that the only orbital motion present, there was a huge orbital effect which turned up immediately, but that of course was the Earth itself in orbit about the Sun. That produces a big Doppler shift in the timing of the pulses. Having subtracted that out from the data, there was nothing then left, or if indeed there was orbital motion, it would have to be in an orbit so distant from a star that life, as we know it, wouldn't have been possible. And that took me, as I said, the first pulse was about November the 28th. I was doing Doppler shift measurements from the first week of December. I think I started about December the 12th, 11th, and I did that right through December until early January. And it took me that time to prove that there wasn't any additional Doppler shift apart from the motion of the Earth. That eased my mind quite a bit, because it's not physics anymore. If it's intelligence, it's a different line altogether. But at the same time, Jocelyn had been analysing past data, because it was likely that if we discovered one, there were others of these sources on the charts. And she came up with 3 others, which eventually she checked, and they turned out to be pulsars too. So it would perhaps be a bit unlikely that you'd suddenly start picking up intelligence from various directions in the sky, intelligent signals, but not necessarily so, because, I mean, if it's there, there are lots of planets around. So anyway, my mind was a little bit easier at that stage, but I had discussed with Martin Ryle before Christmas, when I didn't know the answer, what on earth are we going to do with this data if it turns out that intelligent signals are a likely explanation? And you can't just publish it, and you can't just release it as a news flash. We thought we'd work through the Royal Society in London, actually. We'd inform them and get them to consider it, and perhaps have some national statement about this. But it was too big a thing to be handling on ourselves. And should the evidence have been pointing towards intelligence, we would have then, without making it public, approached the Royal Society and say, here, we've got this, what do you think we should do with it? Luckily that never happened, because by about the first week in January, as I was saying, I had found no Doppler effect for planetary motion, and Jocelyn had come up with 3 others. So we then started to hunt for scientific conventional explanations, and I went to the library and looked up books on midget stars and so on, discovered that white dwarfs and neutron stars were possible solutions, and we had enough to write about without saying what they were, but I mean, just describing the work that had been done was quite a lengthy job, and I wrote a lengthy later letter about all this, and hinted at the end, plausibly, this could have been oscillations of a white dwarf or a neutron star, and we left it there. But of course that was when the balloon went up, and we kept our mouths tightly shut, for which the Americans criticised us roundly later, but I don't repent for a second.
Why
I gave
did
a
they
lecture
criticise
in the old Cavendish, because I felt it was unfair to local people not to hear about it from the horse's mouth rather than read it in the scientific press. That isn't right, because people knew that something had happened, but they didn't know what it was that had happened. I mean, half a dozen of us knew, and so I gave a seminar in the Cavendish. It was meant to be a group seminar for about 30 people, It turned out to be more like 100 because the grapevine worked and people like Fred Hoyle were there. And I gave a seminar which let the world know what was going on.
Which room did you give it in? Do you remember?
In the Maxwell Lecture Theatre,
Yeah.
which I knew well from my undergraduate and my early teaching days myself. A lovely room to give a lecture in.
Exactly, yes. And it would fit 100 people in.
Oh yes, yes.
Just in passing on that one member of the audience who was there, Fred Hoyle,
Yes.
what were your relations with Fred, and how can you say anything about him? The bluff Yorkshireman?
My relations with Fred were quite reasonable in those days. I'd met him on committees. He was a wonderful person to listen to when he gave a lecture. He'd always had something interesting to say, and there was a lovely institution then at the old observatories, which is now called the Institute of Astronomy. When there were seminars with a lovely English tea laid on by the astronomers' wives. It was really old-fashioned, and you had thin brown bread and butter and slices of homemade cake before the seminar, which always actually attracted a good audience. It was a sensible thing to do if you wanted to publicise your work and so on. But whenever Fred Hoyle gave a talk up there, the Observatory Club it was called, I've just remembered, whenever Observatory Club had meetings, they were always full, particularly full when Fred was speaking, because he always had something new and interesting to say. You didn't always believe it, but it was a bit of a, he was always good fun to listen to. And he raised a very pertinent question. He was about the first to raise a question from the audience. He was sitting in the front row in the old Cavendish. And he said, well, what you really want is something in between a neutron star and a white dwarf. Now, I won't go into the reasons why he said that, but it was a very sane and sensible remark, actually. It's to do with the densities of the stellar density. A neutron star would have really given rather more rapid flashes, and the white dwarf rather too slow. And he said, what you really want is something in between, which was actually a very sane, sensible remark. But after my lecture, the positions were, Jodrell Bank knew of the positions. We told Jodrell Bank, and they got onto it straight away and confirmed it instantly, and did things that we couldn't do because they can track it across the sky. We could only see it as it crossed meridian for 2 or 3 minutes, a few minutes each day.
And you announced it formally in a paper, a joint paper in '68.
In Nature. Yes.
In Nature in 1968,
yes,
with five people's names on it.
Yours
yes. First.
Yes. Then Jocelyn, my student. Yes. And then the others who'd been involved with the follow-up work.
Martin Ryle as well?
He wasn't.
No,
he wasn't on that.
No.
Scott, actually before Scott and Collins. Paul Scott, who's still doing radio astronomy, he's retired, living in Cambridge now, but it was confirming our signals on another radio telescope at Cambridge, which was an important part. And the Nature letter actually discussed quite a lot of work from observations not just made with my array, but with telescopes at Lord's Bridge. I mean, we went into quite a lot of theory and to get the distance measurement and so on. There was the rate of frequency drift, pulse dispersion. I won't go into the details now, but it was rather hectic 2 or 3 weeks before Christmas when a lot of people were doing slightly different things at Lord's Bridge, and to condense that into a readable Nature letter and name the people who were responsible for it. That was my job, and Paul Scott was in charge of the other observations. No, I'm sorry, there wasn't John. There were 5. John Pilkington. I've forgotten John. Pilkington.
Oh, Pilkington.
Yes. So there were various bits of work to describe, and that's why there are 5 names on the Nature letter. But it was published within about 2 weeks, I think, which was a pretty good record for Nature in those days. So it wasn't kept secret from the world for very long. But I think that was the right thing to do. I mean, I don't think I would have handled that differently. The Americans said, oh, you should have told us much sooner and all that sort of thing. But they were jealous.
You may or may not want to comment on the sequel, which is the Nobel Prize, 1974, because you must have been enormously pleased and excited to get it with Martin Ryle. but as you know, it led to a lot of controversy.
Yes, yes.
As I understand it, the Nobel Prize was for both of you for your general spread of work, of
Yes.
which pulsars was one part of your
Yes.
work, and
Yes.
Martin's was different work.
Yes.
And that is the reason why Jocelyn wasn't part of all this. Is that roughly right, or?
Yes, I think that's right. I mean, when I look back on that, Jocelyn was an excellent student in the sense that she was a really hard worker. She was very well organised, and to keep up with the flow of paper coming from the pen recorders was quite an achievement. And she was very good in the sense that she'd put a lot of effort into constructing the telescope. She was not afraid to roll up her sleeves and do hard practical work under rather unpleasant conditions occasionally at Lord's Bridge. But when it comes to the design of the experiment, just what observations to make, and the follow-up work, I mean, she did the record analysis very well, but she didn't initiate in the sense that she set up anything herself. She was acting really under my instructions all the time, and I think another student would have done just the same. We get jolly good students in Cambridge, and what particular aspect of it, she was sharp and diligent to notice there was something going on in the first place. But when it came to revealing the first pulse, it was my suggestion that it could be like the sun, and we got to look and see, and set up faster recordings of the different equipment. I mean, she didn't carry on to do that by herself. She did it under my advice. And so, I mean, if you have a ship of discovery sailing, it's normally the skipper who gets the credit. It may not always be correct, but it wouldn't be the lookout on the masthead. Do you see what I mean?
Yeah, yes, I do.
And it's a question of being the creativity and the insight that's gone into the science and the suggestions.
Well, it was part of the animus of the occasion was the timing. I mean, this was the height of feminist interest in university and elsewhere.
Yes.
And it also had a kind of rhyming effect with the Rosalind Franklin business. So, you know, there were various things with. But
well, feminists do tend to pounce on things like this, I'm afraid, sometimes rightly, sometimes wrongly.
What was, you can say this off the record, but what was Jocelyn's own relationship to you after this?
Fine.
She never wrote and said, I should have had the Nobel Prize as well?
Absolutely not. And she's on record as saying that she doesn't think that she ought to have had.
Yes,
I mean, she's done extremely well since, but
she was just a graduate student.
She was a jolly good graduate student.
Right. Well, after this enormous excitement, what then did you do? The rest of life seems a bit drab after that.
Well, it branched off into different directions. I still had solar wind measurements going on at the time of this sky survey, which led to the pulsars, and that continued for a while. And I got a couple of theses, graduate students writing theses on that. But one of the features that we discovered during the scintillation, the sky survey of scintillation, is that when you look at the scintillation on we were using actually about 900 radio galaxies in the sky. We were observing 900 radio galaxies in the sky in a period of 24 hours. We discovered that certain patches of the sky showed much more scintillation than other patches of the sky over our 24 hours, and that these changes changed from day to day. And I realized then that we were actually making maps of interplanetary weather in a certain sense. The scintillation wasn't absolutely constant. I mean, the solar wind is always varying, and the the density of the solar wind is varying from one day to another, and I realized that you could use these galaxies, the data we were getting, to essentially measure space weather, analyze space weather on a day-to-day basis, and make maps of disturbances in the sky. This is a very important aspect of space research nowadays, because there's so much technology, I mean space technology, which has orbiting satellites around the Earth, and the sun can be immensely damaging. Disturbances on the sun can ultimately propagate energetic particles which, for one reason or another, reach the Earth a couple of days later and actually put Earth orbiting satellites out of operation. And health hazards for astronauts who might be in space tinkering with some apparatus, you know the way they do, spacewalks. Astronauts could be seriously damaged by high energy radiation from the sun, gamma rays and things like that, X-rays from the sun. They're a health hazard. And knowing about space weather and what's going on in space is now very important in the whole space game. And America has set up an institute, or more than one institute, to actually make studies of these things. I decided that here was a radio astronomical technique where you could likely be able to predict when damaging conditions are going to occur in space close to the Earth. It takes 2 or 3 days for a solar disturbance to propagate from the sun to the Earth. And the Americans, using current techniques, are not able to predict the arrival of these things very easily. I thought that with radio astronomy and looking at our maps, we could probably help them a lot. And the telescope was actually working until 1994, long after it had done its astronomy, on studying space weather. But as I said, initially the survey was not designed to discover pulsars, it was designed to study radio galaxies, and that work went on for many years. I mean, it did its conventional job quietly with lots of graduate students for several years. I mean, about a decade or so. We made 2 or 3 sky surveys. It takes a long time to actually survey 900 radio galaxies at different angles from the sun, to give you all the information that you can get from scintillation, and that sky survey has turned out to be quite useful. And that, you said, you know, what happened after the pulsars? Well, they were just a flash in the pan. We worked on pulsars for a bit, but the telescope did its normal job, and ultimately I was interested, in fact still am, in space weather, using radio astronomy techniques to study space weather. It was working on that until 1994, when we couldn't run it anymore for financial reasons and for staffing reasons. Astronomy moves on, and you can't keep doing the same thing forever. I mean, that sort of monitoring of the space weather is a job not for a university research group, but for something like the Met Office on an interplanetary scale. And I was hoping the Americans would take it up. They didn't in the end. They preferred to launch spacecraft, but I still think there's work to be done there, useful work to be done by radio astronomy techniques in studying space weather that could be extremely valuable.
I was wondering if you could explain something I came across in the university website, which cites your work and pulsars, and roughly described it as the most important breakthrough in astronomy, roughly, of the 20th century.
What is the most important thing?
But why is it so important?
It opened up a completely new chapter of astronomy. The neutron stars, I mean pulsars, are spinning neutron stars which act like a celestial lighthouse. Neutron stars are tiny stars which weigh typically just over the mass of the sun. They contain as much matter, slightly more matter than the sun, but they're only a few miles across. They're stars compressed by gravity until they're a tiny angular size. They're on the verge of becoming black holes, and in fact Stephen Hawking used to phone me up in those heady days and say how delighted he was with this discovery, because it proved that neutron stars, when you compress matter to that degree, and gravitation will do this for you in the sky, matter enters a completely new state, which is roughly like matter at a density of the atomic nucleus, but it's mostly neutrons. And these neutron stars had been predicted ever since the neutron itself was discovered neutrons were discovered in 1932. And the fact that you might get stars made of neutrons had been predicted, but no one dreamt for a second that you'd be able to detect them, because the stars are only a few miles across, and they're not particularly hot, they're not particularly violent in any way, they are totally dead stars, so how on earth would you detect them? It wasn't thought that they'd ever be detected. At any rate, the fact that we detected them opened up a new branch of astronomy. Neutron stars existed, and they opened the door to doing a whole lot of things. First of all, the study of dense matter. Matter at that density you can't make in the lab. I mean, it exists in an atomic nucleus, but you can't make a lump of it. I mean, if you could, it'd be rather dangerous, because you tend to be sucked in and so on. But they're on the verge of being black holes. As I said, Stephen Hawking was absolutely delighted, because black holes were a bit of a joke in the late 1960s. And he was saying outrageous things about them, which we now know made his fame. But the fact that neutron stars existed meant that black holes, you couldn't really avoid a black hole. I mean, you've only got to squeeze a neutron star by about 10%, and it becomes a black hole. It can't help becoming a black hole. So it confirms that Roger Penrose, Stephen Hawking concept. But it opens up a completely new branch of astronomy, which is the astronomy of neutron stars, which is interesting in its own right. And more recently, the fact that the neutron stars are spinning and act like clocks gives you extremely accurate time measurement in space and in regions where you can actually check out theories of relativity with enormous precision. It's never been known whether some of Einstein's predictions were actually correct or not. Things like gravitational radiation, these ripples in space-time, which can't be detected yet directly. But pulsars demonstrate that these things must exist, because it was the work by Taylor and Hulse in the United States. They found a neutron star, a pulsar, which was in orbit about another neutron star. Probably a pulsar, but we haven't yet picked up the radiation from it. But pulsars, as I said, are such accurate clocks that you can use them for astronomical measurements, such as if you take two neutron stars in orbit about each other, how rapidly are they collapsing? The orbits, if the orbits are losing energy, as they must because of radiation, they'll approach each other. And you can actually measure these effects. The orbital period of two neutron stars decreases. They orbit each other faster and faster as they approach, and these effects can now all be measured. And this opens up gravitational relativistic physics, and that is a big area which led to another Nobel Prize, to Hulse and Taylor. So you see, pulsars are of importance for all sorts of reasons, but they have extended fundamental physics and astronomy, and given rise to a whole lot of new possibilities and tests, some of which are still to be made and some of which are being carried out. But it's just the most exciting area of astrophysics, which happened because we chanced upon these lovely things.
Well, that's lovely. You mentioned there you were rung up by Stephen Hawking.
Yes.
If I could ask you about two of the great Cambridge astronomers, starting with Hawking. I mean, he was in an entirely different kind of field to you. He was a theoretical astronomer, but did you work with him at all, or?
No, only just to chat over the telephone. No, I mean his theories are way beyond my comprehension almost, and I like to find out what's there and let the theoreticians tell me exactly why it's there.
Well, that takes you a bit closer to Martin Rees, then. He was at least a evidential astronomer.
Yes.
How do you assess Martin? Because I've interviewed him, and it's nice people talking about each other a bit in these interviews.
Well, my first contacts with Martin Rees were when he was a young graduate student, and he used to come around the old Cavendish, talking about ideas about what radio galaxies might be, and I always had a great respect for him because his theories were. Well, he always talked about his sort of physics, which meant he wasn't such a highbrow physicist as Stephen Hawking. His sort of physics was the sort of physics that you can get your hands on, and his sort of physics we could appreciate, and his sort of physics led to theories of how radio galaxies work, which turned out to be correct, and he was very influential in understanding the radio maps that Martin Ryle was then making of high resolution, showing you actually what was going on in these active galaxies. And so I've always had a great respect for Martin Rees, and he's extremely clever, and I think now he's pretty wise. He used to think that astrophysics was mostly an American practice rather than a British one, but we didn't like him for that generally. But I think he's over those days now. I think he's an extremely good president of the Royal Society.
Talking of America, were you ever tempted to go to America and work there?
Not to work, no. I mean, I had some offers, but and I have had a sabbatical over there. Yeah, I always enjoy going there, but I wouldn't especially want to work there, I think. I mean, Cambridge was the centre of the universe. I don't really want to be
in every sense.
I don't want to be anywhere else.
Why was that? Why?
Oh well, everybody comes to Cambridge, don't they? And if you want to know about something, there's always somebody around you can ask. I mean, it is such a wonderful place to be. There's so much going on, and I think we're very extremely lucky to be here.
What do you put this down to? I mean, some people put it down to the college system. Do you think that helps?
That's part of it. I mean, I think history is part of it. Cambridge is a lovely place. It's sort of iconic, isn't it? And I think we simply attract the best people, the best young people, and they're the stimulus, and they're the pacemakers, as it were, that keep the place alive, aren't they? And I've always enjoyed our teaching methods here in Cambridge. I mean, when you give a physics course, it's something you dream up as you prepare it, but it's not like following chapters in a physics book, which is the sort of way they teach physics, I gather, in the United States. You know, they do it chapter by chapter, week by week, whereas I'd much rather try and talk about basics in the way I think about it, and you have that one-to-one contact with the young people, which I think there's less of in the United States, quite honestly.
You've done quite a lot of supervising.
Supervising and lecturing, yes. I mean, I think the combination of research and teaching is a wonderful mix. Teaching is a great challenge, especially teaching the bright young people that come up to Cambridge. They ask you awkward questions. I don't think I ever really understood physics, although I got a first class in my final degree. I don't think I really understood physics until I taught it for 2 or 3 years. It's teaching that really gets you into the nitty-gritty of it.
And you enjoy lecturing?
Yes, I do.
Because
I mean, I'm not a publicist. I'm not an actor in any way, but it's the discipline of how do you present something. It's a challenge which I enjoy. I had to lecture the introductory physics in 1976 to anybody doing physics for the natural sciences tripos in Cambridge, so it meant that I had to, the course is now divided between those who are going to go off and be chemists or mathematicians or something. Our tripos system, as you know, is very flexible, But I had to take everybody doing physics in the first year, I'm talking now about 1976, which was about 450 students. And I had to not bore the brightest and not baffle the dimmest, and present essentially, my course was called Concepts in Physics, and teach them a lot of basic physics, at the same time introducing things that they were going to meet later on, and trying to get them used to some of the more difficult ideas of quantum physics and relativity, mixed in with standard things like Newton's laws of motion. And that was a great challenge, and I enjoyed doing that. I did that for 3 or 4 years. But I've always enjoyed the teaching side, because it is a challenge, and as you mentioned, the supervision system, that is, I think, one of the secrets of Cambridge, that close contact between people involved actively with the science and those learning it. And the questions bright students ask you are very challenging.
What about writing? I suppose you, as a scientist, you don't write too much. I mean,
No. I've been too busy, as you might say. I mean, hands-on takes a lot of time, actually, and I've never felt like getting up early in the morning at 4 a.m., to write a popular science book.
Although you're interested in popular science, you gave one of the Faraday Royal Institution Christmas lectures.
Yes. Oh yes, well this is again this presentation. I mean, I love trying to present these exciting things to the general public. I think that's what scientists ought to be doing. I mean, after all, we're spending lots of public money, and I think it's a duty really to try and explain to the general public what it's all about.
I've just got a couple last questions, if I may. One is God. I always ask everyone about God, and whether they, particularly astronomers, it seems interesting to consider what their religious beliefs are. You mentioned going to chapel or church when you were at school, but has God played any part in your life since? Or
Yes, the answer is yes. I mean, I went through the normal teenage heretic episodes, and I didn't go to the chapel very much when I was a student, but you can't help, if you're brought up at an English public school, getting to know the liturgy and the Book of Common Prayer, and it somehow gets into your blood if you go to chapel once a day, and so I love the old music and the James Bible and all that. But I married a clergyman's daughter, and I think that was a pretty influential thing. I got to know about country parishes, and well, I've been a doubter all my life, and I suppose I still am. I do believe in God, and I believe in supporting the local parish church. I mean, I don't know if you know the Church of St Edward's, just over the road here. I was church warden of St Edward's for a number of years, until I moved out to further into the country, because my wife wanted a bigger garden, and I've only quite recently retired from being church warden of my village Anglican church in Kingston, and having thought a lot about it, and people ask you questions, of course, I think there has to be a God. I can't account for the world without a God, and to take the sort of atheist view of Richard Dawkins just seems to me to be total nonsense. I mean, I've read his book carefully, and his arguments fall flat as far as I'm concerned. They're not arguments even. Although it's a popular book. I mean, I think it's a popular book because he's saying what people want to hear, probably. But theoretical physics, you see, brings you into contact. I mean, I think science actually isn't anti-religion in any way, as I'm sure John Polkinghorne, I don't know if you've ever spoken to John, he writes elegantly about these things in a way I couldn't possibly do. But being a scientist and facing up to scientific understanding makes you prepared to believe in another world, and I can't just see the point of the universe unless there's an intelligence behind it, and so you might as well call it God. And when you look at the evidence, it seems to me the evidence is pretty strong too. Thank you.
And the last question is, if you were and I gave this, asked this of a number of scientists, if you were giving advice to a young scientist just starting their career, say at the PhD level,
Yes.
Is there anything particularly you'd say, reflecting on your own life?
Well, only the obvious, in the sense that don't follow the bandwagon. I mean, try and get into some work which is on the boundaries in some sense. When I was starting research, I was late to, as it were, apply for a research posting in the Cavendish, because I hadn't planned to be an academic, and I didn't think, and my tutors didn't think, I was actually going to do well enough in my final exam to justify my doing research, which required a first. So, and getting into radio astronomy was the best thing that could have happened to me, because all the popular research areas, like nuclear physics, like low temperature physics, like crystallography at the Cavendish, these were all very well-known areas. They'd all recruited their potential research students, and there weren't any vacancies except in this unknown area. You know, what's going on? Is it to do with the ionosphere? Is it to do with the universe? What is it? No one knew what radio astronomy was. The name didn't exist. It's just that they're looking at radio waves coming from the sun for some reason. Well, I had the technology and I could get into there and do something. But my advice is not to get into a well-worn, popular subject. Try and choose an area which looks interesting and exciting, about which little is known. I mean, at the moment, who knows, neuroscience or something like that. I mean, we haven't a clue how the brain works, really. So don't follow the bandwagon. Try and get into something where you can make your own mark. I mean, that was another great advantage of radio astronomy. I mean, I could get in and develop my own interests quite rapidly, and the technology wasn't enormously expensive or tricky. And I saw niches where I could actually make an impact. And I think when you're starting research, your first paper is about the most important paper you write, probably. And when I discovered I'd done a little bit of theory which was really useful, I hadn't thought it was all that useful, but Jack Ratcliffe said, hey, you must publish that in the Royal Society. I thought, what? Publish that in the Royal Society? You know, that's a tremendous boost, actually. But starting research is a very tricky time for young people. I mean, I nearly gave it up after a few months because I didn't think it was getting anywhere, to be honest. I wondered whether I'd done the right thing. So it's very iffy when you're a young graduate student, I think. But it's much easier to make discoveries in an area which is full of mystery and not much worked upon.
Well, that is so fascinating, and I want to ask you one more question, which is about, again, advising a young person on work methods. I mean, do you have your good ideas when you go for walks, or when you're having a bath, or do you pace yourself, or do you have any advice on how to think, so to speak, productively? Have you ever thought about this?
It's very hard to analyse, isn't it? No. You've obviously got to be a bit reflective. I think the ideas come to you when you're actually engaged. You want to be engaged in something. I mean, you can't just sit down in front of a sheet of A4 and write down brilliant research ideas. It just doesn't happen that way. Somehow two and two come together and click when you're lucky. No, I don't think I can give any direct advice about how you get inspiration. I'm sure different people get it different ways. But having your head in books all the time, I don't think is a good idea. I think you should I think you should dream a little bit and see if ideas come.
I'll leave you with your dreams. Thank you very much indeed, Anthony. That was lovely.